So good evening, everyone. I hope I am properly audible to all of you. In this session, we are going to discuss a very fundamental uh, concept or technique that is used in computer vision and related application, and it is about edge detection. So we will be talking about the very basic and very traditional concepts that are used in computing the edges. So I hope or like if you have some background, then maybe this is a bit redundant. But otherwise, if you are new to this area, then I hope this will be like very useful for you to understand the basics of design and the related applications. Okay, so this is the way we are going to actually move forward. So we'll first see why do we need to compute edges. So what is the motivation behind computing the edges? Then we'll see, we'll formally define what the edges are, and then we'll see. In the process of computing the edges, we'll see that we use image gradient. So we'll understand the concept of image gradient, and there are some standard operators that are used for computing the edges. So we'll try to look at them and as many as possible, depending upon the time that is available to us. So let's move forward. So just to get motivation for this, just look at this image. And when you see this image, though this image is not completely available, but very well you can identify what this object is, right? For example, in very clearly, you know that's an aeroplane. Similarly, if I show you this image, then very clearly you can tell that this is the image of a deer, right? Then if I show you this image, you can identify that this is actually representing flower. So in all these images that I am showing you, what is available is not the complete content of the image, only some highlighted pixels. And with the help of those highlighted pixels, you are actually able to able to guess what the image is. So here, these highlighted pixels that we are using that we are depicting here, they are basically called the edge pixels, right? In all these images, whatever the highlighted pixels, the white pixels that you are seeing here, right? All these pixels like these pixels are these pixels, all these are actually referred as edge pixels. So we'll formally define what an edge pixel is. But right now we see that with the help of these edge pixels, or collectively they are referred as edges, we are able to identify the objects completely, right? Very well we can identify what the object is being represented by those those edges. So we see that these pixels, which we are calling as edge pixels, or collectively we are referring them as edge, these edges actually provide good amount of information to recognize an object. So in place of, let's say, having this whole image, if you have just the edge part of it, the image which is highlighting the edges or edge pixels of the image, you can actually identify the image that you have. So since you are able to identify the image or the object that you have in your image just by using the edge pixels, there are certain advantages. For example, these edges have very less requirement of the storage. So for example, if you are storing the edges, you need to just store them in the form of, let's say, binary numbers, 0 and 1. So every pixel can be represented by just using 1 bit. Whereas if you are having a grayscale image, in this place, every pixel is actually represented using 8 bits. So you see that there is a drastic reduction in the storage space that is required when you are representing your edges. And also, there's another good thing about them is that these edges are invariant to many image issues. For example, contrast or image illumination or noise. These things actually, if you see the content of the complete image here in the form of grayscale image, as you see on the left, here this appearance, the pixel values will change if let's say the the image is highly illuminated, or it has noise, or the contrast issue is there. So depending upon the environment in which you are capturing the image, you will see that there will be difference in the pixel intensities. But for all those images, let's say the content is the same horse, let's say you are capturing one in where the illumination is more and another where the illumination is less. If you compute the edges, you will find that you will still be able to detect edges in both the cases. One where illumination is less comparatively, and another where the illumination is high. So these edges are actually invariant to contrast, illumination, noise, and that is why again another advantage, and because of that we prefer using edges wherever possible. Okay. So now let us formally define what is an edge. So you can, very simple terms, we can define edge as a boundary between two homogeneous regions. Right? So for example, just look at these images. So I mean, if you just overlap this edge part on this image here, so basically these are the pixels which are defining the edges, right? So on this at this place, you see on this side you have one object, and on the other side you have another object, or you can say on one side you have one type of region and another side you have another type of region, and in between you have the edge, which is actually kind of showing you a boundary between these two regions. So that's why we are saying that edge is actually a boundary between two homogeneous regions. Why we are saying that they are homogeneous region? Because if you look at the pixels that are there in this particular area here, all these pixels, they have one kind of nature. And if you see the pixels on the other side of the image, you have another kind of nature, another type of pixels. So across the edge, if you see the pixels, they are, I mean, like their characteristics are different. But if you see the pixels on one side of the edge, then you'll find that they will be similar to each other. So that is why across the edge, I mean, if you analyze the pixels, then they are different in nature. But if you analyze the pixels on one side of the edges, then you'll find that they are very similar. So in what way they are different? So that you can say they are distinct in terms of the intensity, and they are also exhibiting some kind of uniform or homogeneity among the pixels which are falling on one side of the edges. Okay. Now, how do we define the edge? So if you, let's say, the image like this here, where one part is on one side you have complete black pixels, and on the other side you have complete white pixel. Now, if you just take the intersection of it, like you just put a line here and then see the intensities that you have below this line, then you'll find that this, and if you plot that line, you will find the line will look something like this, right? So at edges, you will see, as we just discussed, that whenever you have an edge, it is the boundary between the two homogeneous regions. So on one side, you are going to have one type of intensity. On the other side, you are going to have another type of intensity. So at the place of edge, you are actually going to have transition. For example, here on one side, you have black. On the other side, you have white. And at the place of edge, you have this transition where the intensity is getting changed from one value to the another value, right? This is a place where actually you are moving from one region to the another region, crossing the edge. So this type of edge is called the step edge, right? Because I mean, you see a step kind of thing is there. On one side you have this profile, and then again you have on the other side you have this profile, and like that you have two stages, and like there is a step between them. So this kind of edge is called step edge, where on one side you have one intensity, and on the other side you have another intensity, and this is a very ideal case, but practically you will see a transition like this. So whenever you are seeing a place in your image where I mean, there's an edge and you are moving from one side to the other side and the intensity changes. So in that case, the change will be very gradual. It won't be sharp like this as you see here. It is going to be gradual like this as you see in this case. So, and this kind of edge is called the step edge. So what is the goal of edge detection? So obviously the goal of the edge detection is to identify, in given image, identify those pixels which are representing the edge pixels, or I mean, we can say the pixels which are representing the curves, line segments, or the contours, right? So these are basically those pixels which are defining the boundary between the two homogeneous regions. So goal is to map any 2D image, a 2D array, which is this one given, to this kind of image where at every pixel you're telling whether it's an edge pixel or it is a non-edge pixel, or this pixel is part of some curve, line, or segment, or it is not part of any line, curve, or segment. So how to detect the edges, right? How to find out what are the places where you have the edges. So it's a very simple idea. So you see here that at the edges, you have some transition. For example, if you're saying that this is the boundary of the object, then across the boundary of the object, let's say if you move from this side to this side, then when you are on this side here, you have one type of intensity, and when you have on the other side, you have another type of intensity. So at edge, you will always see that there will be a change in the intensity. On one side, you will have one type of intensity, and other side, you will have another type of intensity. So if you have some way to compute or identify this change, then by detecting that change, you can identify the presence of edges. So the change is nothing but the you can say change. I mean, change is nothing but the difference, or you can say difference is nothing but the derivative. And derivative, when you are computing, let's say you are in 2D, so you can have, let's say, the area like this, and then you want to find out the change when you are moving from one side to the other side. So here there are two possibilities of movement. One is that you move from this side to this side, right, horizontal, and you move from this side to this side, so vertical. So when you find out these changes and you put them together, that basically defines the gradient at that particular place. So let's say delta I is the image. So delta I by delta x, or delta I by delta y, which is actually computing the difference or the change in x and y direction. These values, if you put together, this is called as gradient. And by computing the gradient, you can find out at any particular pixel what is the change you have in x direction and what is the change you have in y direction. And also we'll see that with the help of this, you can find out what is the resultant gradient or resultant change. Here, these are individual changes in the direction of x and y. Now, if you can combine them, then you get the combined change. And once we get the change, then you can very easily visualize here that when you are going to compute the gradient of this image and going to, let's say, represent this image, all those pixels where you have high value of gradient, those pixels are going to be those pixels where edges are present, right? Or the edge pixels are there. And the pixels, the areas where you don't have any gradient, that means those are the areas where there is no intensity change, there is no gradient there, or alternatively, you can say that there is no presence of edges. So to compute the edges in any image, what you have to do is simply you can compute the gradient at every pixel, and then find out what are the places where gradient is having some value and what are the places where gradient is low, or let's say equal to 0, and that way you can compute the edges. Okay, so with the help of derivative and this gradient, we are going to do this. So you can say that computation of edges is nothing but computation of image gradient, right? And gradient is actually a directional property, because this is a kind of vector. You have two values here, one in the x direction and another in the y direction. So this is a gradient. I mean, this is sometimes denoted like this, del I, right? This kind of triangle, and then I. So this defines the del I, and this is nothing but the gradient in the direction of x and gradient in the direction of y. So this particular quantity is actually a directional quantity. So I mean, when you have a directional quantity, then the direction quantity will have both magnitude and the direction. So here the gradient has a magnitude and also has direction. So yeah, so here, I mean, as I mentioned, this is defining the gradient of f. That means f is the function. You can say f is image. Now you are computing the change in the x direction and change in the y direction. Now let us see a few cases and then see what is the practically the gradient value we get here. So in the first case, we are seeing that the y is gradient in the direction of y is 0, and gradient with respect to y is 0. Gradient with respect to x is something. All right. Similarly, here gradient with respect to x is 0. Gradient with respect to y is there, and in this case you have the both values non-zero. Now here, why we are getting this value as 0? Because in this image, when you are moving in the x direction, there is a change, right? Gradually you see that intensity is increasing, but when you are moving in this direction, there is no change, right? or when you're moving here in the same direction, there is no change, because I mean, whatever intensity of the pixel you have here, the same intensity of the pixel you'll have here, right? So there is no change. So the gradient value is similarly in this particular case, that there is no gradient when you are moving in the x direction. So that is why that x part is 0. And in this particular case, you see the pattern when you are moving in this direction, x also changes. I mean, gradient intensity value in x and y both changes, and that is why you have both non-zero values here. So, I mean, you can compute the gradient direction also, because gradient is, as I said, gradient is a it's a directional quantity. So by using the x and y components are, I mean, the two components that are available in the gradient, you can compute the theta, or the orientation of the h. So here, theta is nothing but tan inverse of gradient in y direction divided by gradient in x direction. So that way you can compute theta. So every place here, and computation of the magnitude is very simple. I mean, like when you have, let's say, vector as a comma b, and you want to compute its magnitude. So this is nothing but a square plus b square under root of that, and that's what exactly we have done here. So whenever you have to detect the edges, you have to first compute the gradient, as you're seeing here, and then on the gradient you have to compute its magnitude and the direction both, and with the help of that you will see the lot of information you can get about the image. So here, this is one example where we are showing the gradient direction in an image. Here you see that this is the area and edges here, and this direction is the gradient direction. So gradient direction is the direction actually which tells you the change in intensity, direction in which there is a change in the intensity, or maybe we can say highest change in the intensity. So now here you see you have, when you are saying you are computing del f by del x, you are computing the change in the x direction. Here you are computing the change in the y direction. Now, if I go back here and then tell you, so in this case, we see that here, let's say in the first and second images, in the first image you have this value 0, y in the direction of y there is no change, right? And so you will find that, I mean, here you don't have any change in the x direction. Here there is no change in the y direction, the previous case. So always these edges, I mean, I think it's easy to visualize that these edges are actually always perpendicular to the direction of the gradient. For example, here you see when you are moving from, this is the edge, right? This is the edge. So when you are moving from one, this area is there, and then this part is defining the edge, because from on this side there you have one type of image, and on the other side you have another type of image. So here there is a transition. So always on the edges, you will see the change in the, the direction of the gradient will be always perpendicular to the direction of the edge. For example, if you have edge like this, that means that when you move from this side to this side, then only you will see the change in gradient. So that is why always gradient is perpendicular to the direction of the edge. So if your edge is like this, then the gradient is going to be this, right? And that is true for every pixel of the image. Wherever you have edge pixels, at that particular pixel, if you compute the gradient, it is going to be perpendicular to the direction of that edge pixel. Okay. So now we have concluded here that when you are computing the edges, it is same as computing the difference in the intensity at different pixels. Now, how to compute the difference? So one way is like you can define this difference in the form of derivative. Derivative is nothing but the differences that you calculate. So here we can say, if you, let's say, want to compute for function f, you want to change with respect to x. So then you can say that you can actually compute the derivative of that function with respect to x, and derivative is defined like this. Well, how do you define the derivative? You define the function value at x. You define the function value x plus delta x or dx, and then divide this change by the dx, and that defines the uh, derivative of that function, right? Now, in place of this, we can also approximate this derivative by writing this. In place of fx plus dx minus fx, we can say fx plus dx minus fx minus dx. So it's something like earlier, let's say you have an image like this. Earlier, you were saying to compute the derivative, this is your fx and this is your fx plus delta x, right, or dx. So to compute the change, you are subtracting fx to this and then dividing by dx. Now you can also do like this, that this is fx plus dx. That way you can say this is fx minus dx. So you can compute the value by subtracting this value to this value and then dividing by the total length that you have here, and which is twice of the previous case, 2dx. So you can approximate this derivative by like this also. And similarly, so here we are talking about the 2D, 1D differences. Now you can have the 2D differences as well. So if you're defining the 2D differences with respect to image, it is actually going to be, the formula is going to be something like this. So now when you are computing actually the differences in your image, you are basically trying to compute the finite differences. And to compute the finite differences, I mean, we cannot use these symbols like as used here, like dx or things like that, because dx and all these things will work when you are in continuous domain, right? In the discrete domain, you have to approximate your derivative with the help of finite differences. So here we see what is the equivalent we get for the given filter in terms of the finite differences. So you can see this figure here. What you say is that you are basically, let's say you have a row like this here. There is something in between. Its coordinate is x comma y, right? This one is x plus or x minus dx, and this is x plus dx, right? So basically, when you are saying that you want to compute the difference in x direction by subtracting fx plus dx minus fx minus dx, right? I'm just not reading y because y is like fixed. So to compute that difference, you can have a very simple way of this with the help of filters. So your ultimate goal is to consider the pixel intensities here, and you should subtract this to this, right? So let's say you employ a filter like this, -1, 0, and 1, and you apply that on image. Let's say this is the image where you apply this filter. So this is, let's say, image fx, y. This one is fx plus dx. This one is fx minus dx. So now if you compute, I mean, if you multiply these respective values of the filter to the underlying image and then aggregate that, what actually you will be getting here is uh, this this function minus this function, right? Because when you are going to apply this filter on the image, one is going to be multiplied to this, 0 is going to be multiplied to this, and -1 is going to be multiplied to this. So like that, you will see effectively that this is going to give you fx plus dx minus
Hello, Suryaprakash sir, are you there, sir? We cannot able to hear you, sir.
Sorry, I hope you are able to see my screen now. So I was just explaining that you have, let's say, the image profile like this, or the intensity profile like this, where on the one side you have one type of intensity, and when you are moving from this side to this side, your intensity changes. So that means this is basically showing, this intensity profile is showing you the change in the intensity. So when you have image like this, or when you have intensity profile like this, and you are computing the derivative of it. So how does the derivative look? So you'll see the derivative actually looks like this. When you have edge like this, then derivative comes out to be like this. So I mean, in general, let's say this is the edge, and we want to see what is the kind of derivative plot we will have. So the derivative plot is going to be from here it is going to increase, and as the edge it will peak, and then it will decrease. So you can just remember, when you have intensity profile like this and you want to take the gradient of it, your gradient actually comes like this. So this is the derivative showing for 1D intensity profile. Now, what about the 2D? So we see here, this is the original intensity profile. Now you are computing the derivative. So in the derivative of the filter, in the derivative of the image, your edge exists actually at the place where the derivative peaks. Now you can compute the second derivative as well. For example, this is the first derivative. Now you're computing the second derivative. So in the case of second derivative, this one, you are identifying the edges by zero crossing. So what is the zero crossing? So you see when you have this intensity profile, and then you are computing first derivative. Corresponding to that, when you compute the second derivative, at the place of edge, you have intensity as zero on either side of the edges, on either side of the edge pixel. You will see that there will be some non-zero values, or some some non-zero values, and at the place where edge is there, you will have exactly zero value. So when we are computing the edges using the derivative, if we are using first higher order derivative, first order derivative, then the location of the edge is actually the location of the peak that you have here. And in the case of second order derivative, if you are using second derivative base operator, then location of the edges, this particular point, which is called the zero crossing, because here when you are applying the Gaussian on your input image, it actually converts the image to second derivative. When you compute, it looks like this. So corresponding to the peak in the first derivative, you have actually a place like this in the zero crossing. So when you are computing using the first derivative, you have to consider the image, compute the first derivative of the image, and then in that look for the highest value in the output. And when you are computing it with respect to zero crossing, then you compute this by identifying the zero values in your output. Okay, so based on this discussion, I mean, up till this point, we have discussed that to compute the edges, we have to take the change in the derivative, I mean, change in the intensity. That means we have to compute the derivative. And when you are using the derivative could be first order derivative, or it could be second order derivative. So in the case of first order derivative, you are basically going to compute. I mean, if this is the area that you have corrected, I mean, part of the image that you are considering for computing the difference, then in this case, to compute the first derivative, you are going to actually subtract this value to this value, fx plus here you're saying fx plus delta x, or in terms of discrete, if this point has let's say coordinate x comma y, then this this coordinate will have x plus 1 comma y. So here if you compute x plus 1 comma y, you will find this value and yeah, this value is x plus 1 y, and then similarly you can write this also as f x minus 1 comma y. So now if you're applying a derivative or difference operator, you're multiplying this whole thing in by minus 1, 0 and 1, then you'll see that you will actually get the difference. So that is why you are computing, when you are computing the edges, you are computing these differences, or you can say equivalent matrix to those differences, and then you're applying throughout the matrix to compute the edges. Now here one thing we need to understand that to compute the derivative in the x direction or in the y direction, you just need three values, right? You can say minus 1, 0 and 1. And whatever the underlying intensity values you have from the image, you just multiply first value by 1, last value by minus 1, and then calculate the value. That is going to be the change in the intensity at that particular place. So now when you are computing the intensity, you can compute change at one place only. Like for example, this is the image. Now this particular place is the place where you are trying to find out what is the water percentage or what water, I mean like, I mean, in some sense, you're trying to compute the change, let's say, in terms of the intensities. I mean, we're talking about the images, so we, in terms of intensities, we are going to get that change. So now to compute this change, this one option is that you consider this intensity and this intensity subtract. That means you just consider this kind of operator or filter. Now, you can also do one thing, that if you want to compute the change here, just don't compute the change here. You also compute the change in this pixel with respect to this here. So that means you can add one more minus 1, 0, 1 here, so that this gives you the difference of difference with respect to this row. Now again, you can say, let's say another area here where you're trying to compute the difference. So if to compute this difference, you want this difference and minus this, I mean this value minus this value. So this which means you trying to add minus 1, 0, 1, 1 more time. So to compute the gradient, to compute the intensity difference at this place, what we have done, we have computed the difference here, we have computed difference here, we have computed difference here. At three places, we have computed the difference. Now, idea here is that you can just take the average of these three and then conclude that, or use that as the average of this particular pixel, right? So here idea is that in place of relying on the central pixel to compute the gradient, you can just rely on one row up, one row down, and then based on that you change compute the difference, and then take the average of that to compute the gradient value. And this is expected to be better as compared to the previous case, because where we are just using only one row or one column. This is going to be better because here we are taking the three differences and then averaging them and computing the final difference based on them. So it is very less. There are less chances that your filter will be, I mean, your image will be corrupted at all those three places, and you'll get wrong estimation. So in all these filters that I'm going to tell you, this is actually, they are all defined in terms of 3x3 matrix, where in place of using only one filter like this here to compute the difference in the image, you are computing the difference in the image with respect to this row also and with this row also, and then based on the average of the three differences that you get here, you compute the intensity of the original pixel. So all these, there are some operators where we define this kind of matrices and then we use them for computing the edges. So this kind of matrix where you have -1 in the front, 0 at the middle, and 1 at the last column, this is called the pivot operator. Now, in this case, we are talking about the Sobel operator, which is very similar operator, but now here only difference is that this one here gives more importance to the central pixel and less importance to other pixels that you are considering. So in your image, let's say this is your image, big image on this image 3 class 3 filter is kept here. So if this filter is telling you, I mean, if you want to give, I mean, I just said earlier, you are computing the difference with respect to this row, difference with respect to this row, difference with respect to this row, and then you are going to take the average. Now, in this average, you are giving equal importance to all the neighbors. Now, here, this theory says that give more importance to the difference that you are getting with respect to the pixel where your this computation is happening, and less pixel to other surrounding rows. Right? So here, main computation is done for this, so we are giving -2 weightage to this, and less computation is, like less importance we can give to these rows here. So we are giving weight. You can say one there, right? I mean, like same -101 that we were using earlier. So in the case of Sobel operator, the difference between Sobel and previous operator is that this particular row is different in this case. We had -201, it was -101. And this change, the idea behind putting this higher value compared to this row and this row here is that we are basically relying on the difference that we are getting with respect to the central pixel compared to its neighbors. So this is the matrix, standard matrix Sobel operator, you can say, which is used to compute the gradient in the image, but this is actually used to compute the gradient in x direction. Right? When your movement is from left to right, that is what this Sobel operator is going to tell you. Now you have gy, which is the which gives you the change in the y direction. Here also, with respect to this change, we have more weightage, and with respect to these two changes, we have less weightage. So these are the standard operators defined in terms of matrix, and with the help of these matrices, you can compute the edges by calculating by integrating the image by these filters, and then by, let's say, using suitable thresholding. We are going to see that later. Right, now this is a Privet operator, Robert cross operator, and here the difference is only in terms of the matrix size. Yeah, and also the difference is with respect to the with respect to the direction in which you are computing the gradient. So in the previous case, we computed our gradient with the help of by computing the gradient in x and y direction. Right? This for the image, and you wanted to compute the difference here. So you computed how much is the difference if you are moving this side, and how much is the difference if you are moving this side, and then based on that you are calculating the gradient. Now, in place of horizontal and computation of horizontal and vertical gradient, this particular operator is saying that take the difference in the diagonal. Like, see what is the difference in the diagonal values here. See the different the different diagonal values that you have there. So here, the direction of the gradient is actually different. Now, we are computing the gradient in the direction of diagonal. Earlier, we were computing the gradient in the direction of x and y axis. So in the Robert class operator, there are two changes. One is the size of the filter. It is now 2 + 2. And second is where you are actually, like these directions are not the standard direction in x and y direction. They are in general. Okay, so let's see one example where this computation is being done, and then based on that we get the gradient. So let's say this is the image where you want to compute the gradient. So to compute the gradient, what we have concluded that we can directly make use of this filter. This filter gives you the difference between the items that are required to compute the gradient. So here you put this image here. When you're applying this filter, or this matrix on the image, what we do, we keep the image there we keep this filter on the image there in the there, and then multiply the respective values by the filter values, and then aggregate that, and that gives you the required value. So here, with respect to first one, we are getting, let's say, the 27 values, right? -27 we are getting here. Similarly, -21 7 you are getting when, let's say, you're considering this one. So when you are applying this filter, you have to put the filter on the image and then you have to multiply the corresponding values and then you have to sum that. So application of this filter is giving you -20/7. Similarly, when you are applying this filter to this pixel, again it is -27. So in all the cases you see that the 127 filter size is sorry, 27 is the filtered value coming up is coming. Similarly, when you are moving this filter from this, let's say this place to the another place, you can compute the same thing by using this filter and then put that here in the output image. Now you see in the output image, wherever the edge was there, you will see non-zero values here, and wherever the edge was there, there are some zeros there. Okay. So this was the output when we computed this with respect to when we computed the gradient or the derivative with respect to these filters, then we are getting these change in the intensities in x and y direction. So here, whenever you are computing the gradient, you are computing the gradient in x and y direction, but normally we'll aggregate that by using the technique that we use for computing the gradient of a vector and then use that. So in this particular case, when you are applying in the x case, in the x direction, you are getting these gradients. In the y axis, in the y, I mean, when you are realizing things in the y direction, you are getting these changes. So this is with respect to x, that means change in this direction, and then here you are talking about the change in this direction. So in your image, if you see, when you are moving from left to right, top to bottom, or bottom to top, there is no change. Right? Everywhere you have 0, 0, and that sorry, I mean the same value, right? In this whole column 9 is there, in the whole column this 9 is there, here also whole column 9 is there, here all 0 is there. So if you're moving in this direction, there is no change, and that is why you see that in the y vertical case, your gradient is I mean like 0 value, right? So here you have non-zero value, then here you have 0. Now if you have to find out the resultant gradient, then for that you have to take the consider the gradient in the x direction and gradient in the y direction, and then you have to aggregate that. You have to compute the resultant gradient by using this this formula, right? This is the formula if your vector is gx comma gy and you want to compute its resultant gradient, then you have to take the square of this plus the square of this and then under root, and that's what we have done. So here consider this -27 square plus 0 square, so 27 you get here. Similarly, -27 plus -27 square plus 0 square, you get 27 here. Like that, you compute the gradient values, and now once these gradient values are available, then with the help of them, we can do the edge detection. So here you see, this is the example where we are using the Robert cross operator. So let me just move forward. So you see the application of computation of gradient in a natural image. So this is the very first image that you see is the original image. This is the horizontal. I mean here we are computing the horizontal gradient and then plotting the image here. Here we are computing the vertical gradient and we are plotting the image here. Now you can see that in the images, in the gradient where you are talking about horizontal calculation, you have, I mean, when you are moving in the horizontal direction, you are basically highlighting the vertical edges. So if you can see in this image carefully, all the edges that you are seeing, they are like vertical like this, right? For example, you see the edges here, or edges here, here, here. And if you just look at the places like this, right, where gradient change in the y direction, right? When you are moving in the y direction, you may see the change there, like here. This is the part of the image. So when you are moving in this direction, then only you see the change. If you are moving in this direction, there is no change. So when you are comparing the horizontal gradient, we see that the vertical edges are highlighted, and when you are using the vertical gradient, in that case, horizontal edges are highlighted. So you see, when you are comparing the vertical gradient, all the horizontal edges have been have been actually highlighted. So by looking at the horizontal and vertical gradient, you can find out like the places where uh, gradient change is there when you're moving in the horizontal direction or in the vertical direction. But of course, when you are computing the edges, you have to combine these two. Both you have to combine. You have to combine the resultant gradient, and then based on that, further processing is going to be done. So here we see one example where this whole computation of the gradient is being done, and then with the help of that, the edges are detected. So let's say this is the image, and in this image you have computed the gradient in the x direction and also gradient in y direction. So this is, and then you have computed the resultant gradient. Now, I was highlighting that when you are computing the gradient in the gradient in the x direction, vertical edges are highlighted. When you are computing the gradient in the y direction, horizontal edges are highlighted. But now if you take the aggregation of these gradient, then the true edge you'll get the true position of the true edge. For example, here, even though this particular part here, neither the change is in this direction nor in this direction. I mean, good change. Basically, the change is in both the directions. I mean, when you are moving in the x direction, there also change is there. When you are moving in the y direction, then also the change is there. So when you are plotting this image based on the resultant gradient, then it is going to highlight all the true edges. For example, even though these are tilted, but they will get highlighted because here you have taken into account both change in x direction and change in y direction. So that is why you are getting the true reflection of these. Now, once we compute the gradient, now we know that here, I mean, in this image, wherever the gradient is high, those places are, I mean, represented here as represented in terms of white pixel. So if you want to find out what are the white pixel means high intensity. So if you want to find out what are the pixels where the edges are there, then you can simply take this image and then do the threshold, right? Because these all white pixels that you see here, they are representing the edges. So if you just take this image and then do the thresholding, then it will highlight only those places where you have the intensity is more than that a particular threshold. So this actually gives us the image. This gives us the edge image, right? Now here, depending upon what kind of threshold you are using, you may see that more or less details are there. For example, here we are using lower threshold. So even small, weak edges are also appearing, for example, here or here, right? Now, but if you are increasing the threshold, then you see some of the edges are disappearing. You see, some of the edges are disappearing. Like here, in this particular case, in the lower threshold, you see something here, but in the higher threshold, you don't have anything. So basically, if you are increasing the threshold, then only those edges will survive, which are strong edges. That means where the gradient is high. So you can actually you can differentiate between the edges in terms of strong edges and weak edges. The places where you have good intensity change, high intensity change, then corresponding to that you will be getting strong edge. And other on contrary, where you have less change, less value for the gradient or less value for the difference, then that there you are going to get like weak edges. Right? So strong and weak edges you can identify like this. So when you have lower threshold, strong and weak both are visible. Now when you have higher threshold, then only strong are visible. So here there are some outputs where the standard operators have been used and then the edges are being shown. So for example, you see this is original image, and on this when Sobel operator is used, this is the output we get. And when Sobel operator is used on this image, this is what we get, right? So up till this point, whatever we have seen, there we were using the first derivative, right? First derivative we were using, and then based on that, we were computing the edges. So in the case of first derivative, as I said, when you apply the first derivative on the image and then try to compute try to locate the edges, the edge locations are those locations where you are going to have high value for the derivative. But in case of if you are relying on the second derivative, then in the case of second derivative, the index, the image is the edge pixel is being represented by using this zero crossing, where you have a change in the intensity profile. On this side, you have positive, and in that side, you have negative, and there's some intersection here. So that particular place is called the zero crossing. So in case of second derivative, first, let's see the first derivative. So in the case of first derivative, we are looking for the maxima in the output image that you get after computing the gradient. And in this case, we are looking for zero crossing, no maxima. We are looking for zero crossing. Okay. So, I mean, we have seen many operators where first order derivatives were used, first order filters were used. For example, this one, -101, -101, -101. Like this was one filter that we use. So this is based on first derivative. So when you are applying this filter on the output image, you have to see the location of the pixels where high output has come, or the bright pixels, you can say, and they will correspond to the edges. Now, if you have computed the second derivative, then we will not be looking at the pixels where we have very bright spot. We'll be looking at the pixel where we have zero intensity, right? Or very dull or dark pixels. So the notion changes when we are moving from first derivative to the second derivative. The notion of interpreting the output changes. So in the case of first derivative, we are looking for the maxima, and in the case of second derivative based operators, we are looking for the zero crossings. So now this we are seeing here up till this point, whatever operators we have seen, Privet, Sobel, all those operators, they were all actually based on the first derivative. Now here we see the operator which is based on the second order derivative. We are computing the second order differences. So second order differences in the x direction, second order differences in the y direction. So in terms of the matrix, actually, if you see, if you compute, this is the first order difference. I mean, I hope everyone understands this. This is the first order difference. You have df by dx is fx plus dx minus fx divided by dx. Now, when you're computing the second order difference, it is computed like this: fx plus dx minus 2 times fx plus fx minus dx. So it is nothing but, I mean, you can just simply take the 3 pixels like this. This is your fx plus dx. This is your fx, and this is your fx minus dx. So at the first level, you are computing difference between this and this, right? And then when that difference is available, again, on that you are computing the difference again. So that way you get the get this difference here. How so? Let us compute that. So when you are computing the first order difference, what will be the difference with respect to this and this? It is going to be fx plus dx minus fx, right? Now, with respect to this, what is going to be the difference? It is going to be fx minus fx minus dx. Right? This is first order difference. Now, if you want to compute the second order difference, you have to compute the difference between these two, right? And if you just see, it is going to come as fx plus dx minus 2fx plus fx minus dx, right? So the same as what we have written here. So equivalently, I mean, you can also write this in terms of filters. You can say, if you want to compute this everywhere in the pixel, you can say this filter value is 1. This filter value here, I mean, this particular scale filter is -2, and this filter is 1. So this, if you are applying this filter on your image, actually it is going to give you the second derivative, -1, sorry, 1, 2, and 1 minus 2 and 1. So we are actually going to compute the second order difference in both x and y direction. So here we have the computation done with respect to x-axis, with respect to horizontal difference. Here you have with respect to vertical difference. So if you combine them, actually we get this. So we are making this filter. This row is replaced by this. So you get -1, sorry, +1, -2, and 1. And then you put this here at the middle. So you get 1 and another -1 here. Sorry, another -2 here, and then 1. So if you combine you see that at the corner you have 0, 0. At these places you have 1, 1, 1, 1 here, at all these 4 places, and at the center you have 2 minus, so 2 minus 2 and minus 2, so that becomes minus 4. So if you want to compute the edges by using the second order derivative, then you can actually directly apply this filter on the edges. And this is a second order based filter, so you have to look for the 0 crossing. Right? So you apply the filter and then compute the, find out the places where you have 0 crossing, and then that will be that will give you the locations of the edge pixel. Now here we are directly saying that we are computing the input. We have input image. We are on that we are computing the gradient and then detecting the edges and getting the edge map. But these actually derivative are actually very sensitive to noise. So because of, if you have the noise, then you'll see that you will be getting thick edges, right? And in place of getting a very fine edge for the with respect to the true edge, you will be getting thick edges, and then also you will have spurious edge pixels there. I mean, some of the pixels that you may say they appear and they are actually not the true edge pixels. So because of the noise, you may find these issues, and to handle that, we are normally, so this problem is actually with both, whether you are using first order derivative or the second order derivative. But this is to handle this, we normally use some mechanism to first remove the noise from the image and then apply these operators. Right? So the filters like Gaussian filter or median filter, these kind of filters we first use, and we remove the noise from the image, and then we compute the edges. So with this, I think I would like to stop. So this is like the overall process of computing the edges in case of noisy images. So normally we have a step. This is this first step, maybe second step, and then finally you get the edge map. But here, if your images are noisy, then before computing the edges, before computing the derivative, we are just computing the we are smoothing the image, which actually means we are removing the noise, and then we are doing the computation for the edges. And for that, we'll see that there are multiple options, as I just stated. Gaussian function can be used for removal of the edges, or we can have median filter for removing the noise. And then after removing the noise, we can just make use of the first order derivative based filter or the second order derivative filter for computing the edges, right? So Deepak, shall I stop now? Yeah, and if you have, is there any mechanism to take the questions from the participants? Deepak, are you able to hear me?
Yes, sir. Yes, sir. I was on mute. Yes, sir.
Yeah,
Yes, sir. Yes, sir. Participants can now ask, write their queries in the chat box, sir, so that I can read it out and I can. So, participants, if you are having any queries, please write it in the chat box. So, one question I could see in the chat box is from Pooja. These filters are used in models like Yellow and UNet, or they do use different approach? This is the question.
Yeah, so I think, so let us not go in, even that deeper. So like in CNN and all, you are using something similar filters. So when you are computing the convolution of different CNN filters, in a sense, actually you are using these kind of filters which are highlighting the pixels where you have some kind of intensity profile. Yes. So in deep learning, whenever you are performing, particularly in CNN, whenever you are using the filters for feature extraction, those filters are very similar to what we have just discussed. Like here, we are talking about only two possibilities. As you see, horizontal, one pattern for horizontal and another for the vertical. But in case of CNN, you have several such patterns created, and then based on that, like pixels of some importance are highlighted. Yeah.
So another question is like, is contactless fingerprint biometrics is a good research area to explore?
Yeah, I think, see, everything has some good things and some limitations. So like, I mean, we have so many different types of biometrics. I mean, there's no biometric where there's no work has been done. If you're asking in terms of the possibility of, let's say, publishing the work and something like that, then I think every area has been explored. I mean, like in good length and width. But yes, I mean, comparatively, we'll see less work in this area. So, I mean, of course, you can go for that. Contactless biometric is something which is not as much explored as other areas. And second, I think you can use this. I mean, that you can also show some certain advantages when you are comparing it to some traditional things, because you don't need contact here, right?
Yeah. And the question is, a Kenny edge detector is first order. Is it first order?
Is
I
this?
mean,
So actually, canny edge detection actually uses both. It also uses first order differences and the second order differences, and with the help of that, it actually tries to maximize the computation of the true edges.
and the questions, last question is, smoothing usually causes blurring of the edges. Will it affect edge detection performance?
So what is this? Blurring causes smoothing causes blurring. That is the question.
Yeah, I mean, I think the question is like, is edge detection performance is going to affect if it is applied on a blurry image?
Yes. So yeah, so I think that I mean, I don't know what is the exact question, but there could be two aspects of it. One is that when you are removing the noise, the edges, the image gets blurred, and because of that, the computation of the edges become difficult. That's one thing. And second is, if the image itself is blurry and then you're computing the edges. So in the second case, obviously, if the image is blurred, then you will have challenges in computing the edges, because your edges will not be sharp. I mean, there's no sharp point where you see the transition. But for the first case, where for removal of the noise, we use a smoothing operation, or the Gaussian blurring and all that. So to avoid that, like we are showing here, that you are first computing the smoothing. You're doing the smoothing operation. You're performing the smoothing operation on the image to remove the noise, and then you are doing the edge detection. So when we are doing this, basically we are first blurring the image, which actually degrades the quality of the edges, and then we are doing the edge detection. So to avoid that, there are many operators where we actually combine both of these things. Like I just write some of the operators. For example, you might have heard about the LOG operator, which is Laplacian of Gaussian. So Laplacian of Gaussian is basically a second derivative based operator, but this combines Gaussian with it. So you're not first applying Gaussian and then Laplacian. It actually combines both. And so because of that, we see that we don't see the effect of blurring the edge and then computing the edges. So that effect can be actually reduced if you just combine these two and then make combined filter and then apply that on the image. Okay. Similarly, there's another operator called DOG operator, like difference of Gaussian, which is in a sense approximation of LOG. That also combines the removal of noise and computation of the edges. So by making use of these operators, which are combining the noise removal and the edge detection in it, I think the effect of this blurriness can be avoided.
Yeah. I think, sir, that's it. So thank you very much, sir, for your wonderful talk on edge detection. So I think the participants have benefited from your lecture. So they may also connect the concept of edge detection with the concept of convolutional neural networking later on. So thank you very much for sparing your valuable time with us and delivering a wonderful talk on edge detection.
Thank you, Deepak. It was a pleasure being here.
Thank you, sir.
Thank you, and wish you all the best.
Thank you so much, sir. Thank you. Yeah, participants will move on to the next